All right, dear colleagues, dear guests, welcome everyone to the 19th IFS Seminar. Today it is my pleasure to present Dr. Albert Much from University of Leipzig. Dr. Much specializes in non-commutative geometry and quantum gravity, mathematical physics in general. I had the pleasure to spend my PhD years together with Dr. Much at Max Planck Institute for Sciences in Leipzig. Today it is my pleasure to give him the stage, and he will tell us about non-commutative quantum field theory, a viable approach to quantum gravity. Please, the stage is yours, Albert.
Thank you very much, Yerevan. The pleasure was all mine, by the way, to be your colleague as a PhD. So today I want to talk about this subject about non-commutative quantum field theory. It's a little bit funny because back in the day when we were PhDs, we used to fight a little bit about quantum field theory in curved spacetimes. And I mean, I liked it, but I was not very certain, that it gives you, anything beyond semi-classical or classical, or a little bit semi-classical. And now I'm pretty much convinced that it is actually it is very important, actually. Also in a sense, like whatever quantum gravity is, it has to include quantum field theory in curved spacetime in some limit. Otherwise, this theory, is like missing a big part. And so a little bit just like to describe a little bit like the metaphysical approach here is we say quantum field theory in curved spacetime, is a viable approach and to quantum gravity. And now how do we get one step further? And so what I'm trying to do is so my motivation is to see, does non-commutative geometry connect to quantum gravity? And as I said, quantum field theory in curved spacetimes is a zero-order approximation to quantum gravity that is, I think, agreed upon unanimously. And now the idea is here to fuse non-commutative geometry with quantum field theory in curved spacetimes to obtain a first-order approximation. And the way I want to do it is via deformation quantization, because that automatically gives you basically the zero theory, which is QFT in curved spacetimes, and then it gives you corrections to it, right? So this is a little bit the idea. So what we want to do first, so in order to do it for curved spacetimes, it is not clear how to do it like really for curved spacetime. So we want to generalize non-commutative quantum field theory or the star product, the deformation quantization, from Minkowski to curved spacetimes first. So this is the heavy lift, so to speak. And then we want to prove it complies with certain principles of quantum field theory in curved spacetimes, like the equivalence principle, which is implemented in quantum field theory in curved spacetimes as the wavefront set, or the Hadamard condition, so the micro-local spectrum condition, also called. I will explain this in a bit. And so as I said, why do we want to do this? I personally believe QFT in curved spacetimes provided us with various insights and achievements: black hole entropy, quantum inequalities, description of early universe, even particle interpretation itself was questioned through this theory. So I think it's really an axiom, so to speak. And so any theory of quantum gravity must contain QFT in curved spacetime as a limiting case, I think. This is just like any mechanics theory has to include classical mechanics in some limit. This is the same thing for quantum field theory or quantum gravity, I think. And so I want to see how far can I get with this program and prove a real connection to quantum gravity. Also, mathematically and hopefully physically also. And the real problem, so the cornerstone of the problem is you have this Rieffel product, which is also sometimes called the star product. It is basically an associative non-commutative product. So F star G is not equal to G star F. And you see, if I set theta equal to 0, I integrate, and this is a delta function, basically, this is a cutoff function, delta function, and then I have just a normal product, F and G. So and this theta here is a parameter that is hidden in this matrix basically. And this is, so to speak, the star product or Rieffel product. But this is done for flat space times, or I don't know. I don't know if you mathematicians or not, but you know, physicists say curved space times. Mathematicians say non-flat manifolds. There's always a mixture of notation. And basically, Rieffel proved that whenever you have this smooth actions that commute, basically, which is always, you know, equivalent to a translation group in the end. So translations means, you know, when I multiply two translations, I get a third one, and there is no, so v of x times v of y is v of x plus y. And now the question is, how do we generalize this flat case to the curved case? And so the real technical problem is in non-flat manifolds or curved spacetimes. There are no translations, of course. I mean, because you know, you take a sphere, do a translation, you're somewhere out of the sphere already. So you have to do it in a concrete way, so to stay on the manifold, right? And so of course the natural generalization is the geodesic map of translations, because it tells you exactly how. So you start at a point on your manifold, and then it gives you a vector, and then it tells you exactly how to move along that vector from that point, but stay on the manifold. However, these geodesic maps are a little bit not, so I cannot really calculate with them. And here I want really like to you know, work things out. So this is a little bit also a problem. And one idea was we embed the spacetime in higher dimensional Minkowski, in flat Minkowski, where translations exist. And then we could do something in the de Sitter. And now what I did was take this idea and develop it further for globally hyperbolic spacetimes. So globally hyperbolic spacetimes are spacetimes that are globally hyperbolic. And basically, it means they look like Minkowski. I mean, if you look a little bit on a global structure, there's light-like, space-like, and all these nice features. Furthermore, globally hyperbolic is important in the context of quantum field theory in curved spacetimes, because it gives you the existence of a time direction. So you can at least know, okay, this is the time, and it flows in this way or in this way. And also it the Cauchy problem. So you have let's say a wave equation, right? And the wave equation is well defined on such a, so you have a well-defined Cauchy problem on these globally hyperbolic spacetimes. And now my idea is, let me embed these globally hyperbolic spacetimes into higher dimensional flat spacetimes and work out the translations there and do a deformation with that. So this is like the very broad idea, which of course fails at a certain point, but one can start modifying it. I published this first under the Trump-esque title, Make Deformation Quantization Physical Again, which I thought was funny at the time, but no one else did. And I got even like, some you know, beef with Buchholz because of this. So I had to change this, of course. And now I think it is in a state that things can move forward. So first of all, there's this theorem in mathematics, which is the Whitney embedding theorem, or the Nash theorem, which basically tells you have somehow a curved manifold or non-flat manifold, and now how do I embed this in a higher dimensional Riemannian? And there is a theorem that tells you that for a certain dimension you can always do this, right? And Sanchez and Müller generalized this to globally hyperbolic spacetimes, actually to a little bit a broader spacetime. But basically, if your spacetime is globally hyperbolic, so this is your manifold and this is your metric, then it admits an isometric embedding into Ln. Ln is now Minkowski, higher dimensional Minkowski. So let's say you take the Sitter and you can embed this into higher dimensional Minkowski, or you take I don't know, an FRW spacetime or some Bianchi spacetime, and you can embed this into higher dimensional Minkowski. What does that mean, isometric embedding? Basically, it means there exists a function f where this set of differential equations can be solved, okay? Now, as I am a physicist at the end of the day, I have my problem sometimes understanding all these general, symbols. So I like to go to examples. So I understand that a little bit better. So what is an embedding function, or what is this f? For example, for the case of the sphere, the unit sphere in S2, you know this. This is just x1 square plus x2 square plus x3 square is -1. So if this is 0, then you know this is your embedding function, right? This is the usual way, actually, you study in first and second, third and fourth semester the sphere, right? You get these coordinates, and one is, I don't know, cosine, sine, and so on. And you can do the same for the zeta, of course. There's also mappings for the zeta, and so on. So you see, it is a concrete function, basically, this f. It's a differentiable map, a concrete function that tells you how do I relate the higher dimensional Minkowski space or Euclidean space with my manifold. So basically, your manifold will always be described as a submanifold of this higher dimensional flat space-time. And this helps you calculational wise. This is why, this is that important. Now, the moving in the embedding spacetime, as I told you, you cannot just, if you're in Rn in Euclidean space, you take a point and then you take a vector and then you know how to translate. It's just the point plus the vector, right? Nothing spectacular happens there. And you stay always in Rn. So if you take a point or a vector and add a vector, this is still a vector in Rn. However, for the sphere, for example, this is not true, right? You have a sphere or a circle. If you translate too much in that direction, you're already out of the circle. So how to move in these embedding spacetimes? There's the geodesic map, but and one way to really capture this is by taking the kernel of the differential of that map. So let M be an embedded submanifold of Rn, then the tangent space at the point x is given as the kernel of the differential of any locally defined function f at x. So basically, you take this embedding function, you take the differential of it, and you see when is that 0. This gives you exactly the tangent space at the point x. Note that here you have, so in Rn, all tangent spaces are basically the same, right? It doesn't matter, it's point independent, but in curved spacetimes, it's not, or non-flat manifolds, this is not the case. Now let's do examples. Take Rn -1 and embed it trivially, of course, into Rn. What you're doing is basically, so let's say you take R2 and embed it in R3. What you do is you say, okay, I have my R2 vector and my x3, the third component of my 3 vector is 0. It's always 0. And now you can translate this into this fancy language. Basically, the embedding map or this function f of x is xn. So when xn, so the nth component is 0, then you know you're exactly in your submanifold. The differential of that is just VA nabla A of f. And this is 0 if A is unequal to n, and 1 if A is equal to n. So you see, if A is equal to n, then dxn of xn is 1. And this basically means the kernel consists of all vectors in Rn such that Vn is equal to 0, which is basically, I proved an extremely trivial fact, but in this somehow a little bit more complicated language. I just showed you that the tangent space of Rn -1 is Rn -1, which is already known. But this is, as I said, I like to really do things explicitly. Otherwise, I have the feeling I'm not really understanding it. So basically, take the kernel of this embedding map, which is this trivial xn, and then you get the tangent space, and this is Rn -1, which is well known. You can do it a little bit more complicated, of course. You can take the unit sphere. Now, for the unit sphere, the differential of the map that I gave you before, x1 square plus x2 square, is just xa va. And the tangent spaces are just the vectors. So are all vectors v such that this is equal to 0. So are all vectors that are orthogonal to xa. And this is also basically well known, that the tangent spaces of the sphere consists of all vectors that are orthogonal to the point x, or to the vector x in that sense. So xa va is equal to 0. That gives you the kernel of that, and that's the tangent space. It is important to define these tangent spaces, because what I want to do is I want to take a point, I want to define the tangent vectors on that point, and then I want to move from that point along these tangent vectors, staying in the manifold. This is why I call it moving in the embedded manifold, right? Okay, we have to introduce a small thing here, which is called an orthogonal projector. This orthogonal projector basically takes a vector that is in Rn and projects it to the tangent space with regards to some point of the manifold. So it can be represented by a matrix, an Rn cross Rn matrix, that is symmetric. It is a projector, so p squared is equal to p, and it is self-adjoint, of course. Projectors are self-adjoint operators because they just have eigenvalue 0, 1. And if v is already a tangent vector, then in this tangent space, then p times v is v, so it leaves that invariant. Again, example, okay? For the sphere, this orthogonal projector is just delta AB, so for the unit sphere, delta AB minus XA XB. And here you can do so take XA and multiply the projector on V. So V is some vector in Rn. So what you see here pretty fast is that this projector takes V to the tangent space of X, and X times any vector of the tangent space is 0 because they're all orthogonal in this sphere, right? So this is really for the sphere, it takes this form. For the zeta, by the way, it takes a similar form. Okay, so it's not that different. And the orthogonal projector, if you're in Rn, is just delta. So it doesn't do anything basically, because all vectors are in Rn. So the orthogonal projector is just a unit. Okay, what is important maybe here, what you can take with you is that this projector is a matrix, and it is a smooth map. This will be needed later. And now you can start defining all the things that you need for making differential calculus. So like define the differential, so the gradient. You can define the gradient of f by taking a smooth extension of f on Rn. You take the usual derivative as if you're in Rn, and then you apply the projector back to your submanifold. Okay, so what this thing does is really it's a lift or a pullback, as they say, because basically you forget for a moment that you're on this submanifold. You just behave as you want on the Rn, and Rn you know from school how to take differentials of that, and then the only thing you need to do is pull back or project with this orthogonal projector. So you can define a gradient and then also a Hessian and so forth, right? So this is then just defined by this formula here. And now really, like, what you need, all of this comes together. So I took this from matrix optimization people. So matrix optimization people, they know, in the end of the day, they really need to calculate certain things. So so that means they need to really have a method where they can deal with certain data. So it's all about data. You can represent data by certain manifolds, and now how do you move those data? And then they have developed certain techniques. And one technique that I use is the concept of retraction. And retraction is basically what I explained. You take a point and a tangent vector, and it tells you how to move along from the point along of that tangent vector. So the specific definition of retraction on a manifold is a smooth map from the tangent bundle onto the manifold. Basically, you take such that each curve is basically the retraction, and it satisfies for the parameter t equal to 0, it's your point. And if you take the differential at the point 0, it's your tangent vector. The geodesic map is a perfect example of such a retraction, but you can define a retraction even a little bit more general without the geodesic map. So a second order retraction on a pseudo-Riemannian manifold is a retraction such that the second derivative is 0. This is what physicists call geodesics, right? At the end of the day. But not all retractions that satisfy this condition are the geodesic map. This is what I want to stress out, right? And I'm not opposed against the geodesic map. I just need a notion of a retraction of geodesic map that I can expand such that I can do some specific calculations. And this will help me. And now again, examples. The retraction on a linear manifold is just a translation. And this is basically exactly what I want to generalize to the curved setting, right? In order to move on the manifold. And an example of a retraction, so a non-trivial one, is in the n-1 dimensional sphere is given by this guy. This is not the geodesic map on the sphere, but as you see, if you take the norm, then the norm of this guy will be 1. And that means that this point is on the sphere. So you start on x, and you move it along psi, and then you end up with another point, but that point is also on the sphere. This is what I want to stress out. So this is moving from a point towards a tangent vector, towards its tangent vector in such a way that you get another point, and that point is on the sphere. Yeah, okay. Now, up to this point, are there any questions? You can interrupt me. I don't have that many slides. If you want to ask a question, please.
Basically, is it the vector field on the manifold? And then you just moving along the flow of the vector field?
Yes, in a sense, this is exactly what you do. Correct. Exactly. So if I would change psi with psi t, and t is a parameter, it's exactly that. It's these flows along that vector field. Exactly.
So basically, this is a vector field and corresponding one parameter flow of diffeomorphisms on the manifold.
Exactly. But
You're
in a way,
of the metric, right? This is independent of the metric, right? So because you are not assuming that it is geodesic, so it doesn't bear information about metric.
Right, it is independent of the metric. You're right. In these, I mean, as you see here, I never write the metric because it's actually independent. Correct. All you need is the embedding function, which somehow implicitly depends, of course, on the metric. Correct. Yes. This is also why I like these a little bit, these retractions. Yeah, because the geodesic map depends on the metric. That one, yes. So now you can
ask a question. So do you get any fixed points with it, or does it always move, or can these vector fields stop?
Well, the fixed point is for psi equal to 0, right? So these retractions form a group, and there's a unit in that group as well. But basically, if psi is unequal to 0, you come from one point to another.
Oh, okay.
Yes, but yeah, I should mention this because actually I really literally define the retractions as a group, and the composition is basically done. I mean, or the composition defines the group because the composition maps are associative, and basically Rx of 0 is X. So this is hidden, or not hidden, but I mean, this is basically this condition, right? Rx of 0 is X. So you know that this is your starting point. And yeah, I mean, there actually in these matrix optimization things that there are even fixed point calculations that do not only correspond to this, but I didn't delve too much into that. Yeah, now like we collect all this data and basically using gradients, Hessians, projectors, second order retractions, you have now a Taylor expansion on curves and on these basically geodesics given by this formula, right? It's basically if you think about it, this is just a broader generalization of f of x plus a. So f of x plus a is f of x plus a derivative of f plus a squared divided by 2 second derivative of f. And this is just a generalization on any manifold, basically, that you can embed. So there can be, of course, there can be a bit. There can, let's say, I'm not sure how good these definitions would work if your manifolds has points, and I mean there can be certain things that can go wrong then in that. But we define here we have C infinity manifolds and geodesics on those manifolds, so they can be defined for all the parameters T. I will need one more ingredient before I define this oscillatory this deformation. A Poisson bivector. For those of you who are familiar, this is pretty straightforward. Basically, a Poisson bivector on a smooth manifold is a smooth bivector field, which is basically a smooth skew-symmetric tensor that satisfies this equation, and this comes from Jacobi identity, basically. And you can basically the Poisson bracket and the Poisson vector are connected in this way, right? So if you know that the Poisson bracket. So the Poisson bracket fulfills the Jacobi identity. So f, comma, g, comma, h plus cyclic is equal to 0. Then you get this guy out. And I mean, maybe someone, or I'm sure someone of you is. Oh, sorry, I stopped my screen sharing. Is an expert in these how do you call them? Poisson geometry things. I mean, this Jacobi identity or this Schouten bracket can be actually generalized to covariant derivatives, and there are interesting cases where this can be done, but yeah, I'm not sure of them, and actually I'm trying to find them out right now. So you could basically replace this derivative with a covariant derivative, okay? So if you replace this derivative with a covariant derivative, then and this covariant derivative is the Levi-Civita connection, then this thing automatically holds still, because you know the covariant derivative, the Levi-Civita connection is just derivative plus gamma gamma, and they cancel out perfectly. So it actually doesn't. So whenever you have a covariant derivative equal to 0, for example, you know this is also satisfied. There are certain connections between Poisson bivectors and their covariant derivative vanishing that I think would help physicists more if we would indulge a little bit in them, and I'm trying to do so. Just want to remark this. Okay, now the curved star product. Okay, now we can start a definition and see how far we get with this definition. Fortunately, I mean, this definition, yeah, brought me a long way. Of course, there is a lot of sweat, tears, and praying involved till this worked. But basically, so let the matrix theta be defined as a deformation parameter theta. So this is just a real number times this Poisson bivector. Okay, I define this matrix as this product. Then the generalized Rieffel product of two of these functions. Now forget what this function space is for a second. Is defined basically equivalently like the Rieffel product. Just instead of these translations, I inserted here these retractions. Okay, and x and y are tangent vectors of tzm, and big Z is the embedding point corresponding to small z. So you start with this definition because I always had in my back mind that if I go flat, then this has to be the curved Rieffel, so the usual Rieffel product, right? And it is basically, because then these retractions are just translations, z plus theta x, z plus y, and I have the original definition. Now, what does this non-flat star product fulfill? It is unital. This is something that maybe before I go into, so there are like three different deformation quantizations. There are infinitely many, but like three like very famous ones. One of Kontsevich, which for which he got a Fields medal. So this is like important stuff. So he basically proved that there exists a deformation quantization for any Poisson manifold. So whenever you have Poisson manifold, he proved there is a deformation quantization. Then there's the Rieffel product, which used these oscillatory integrals. The Rieffel product, what differs to the Kontsevich one, is a strict deformation quantization. It means it's oscillatory integrals. You have to use Hermander a lot and all these nice things, right? And oscillatory integrals take care of the convergence. And there is also the Fedosov quantization. That is somehow a special case of the Kontsevich quantization for symplectic manifolds, basically. And this guy here is, or girl, I don't know, is in a sense a mutant between these three. So it's somehow a mixture, but and this mutant was born, so to speak, because I needed it exactly in this way to really apply it to algebraic quantum field theory or quantum field theory in curved spacetimes. And it fulfills things that the star product should fulfill. It is unital. That means if I multiply it with a C number, so that the non-commutative product of a C number with this function is equal to the function itself. It has a commutative limit, which is important for me because, I mean, it is part of the definition of a star product, but also it is important for me in regards to quantum field theory because, as I said, I want to have the zero order be QFT in curved spacetimes, and this will take care of this. And the flat limit, retractions are translations with constant Poisson bivector that turn this generalized Rieffel product to a standard star product. And now, if the Poisson, so let the Poisson bivector have a vanishing covariant derivative. Then the generalized Rieffel product is associative up to second order in theta, and it is explicitly given by this formula. Okay, so you can calculate it. Yeah, the point is that the covariant derivative of this guy has to vanish. Now, so this is the Fedosov quantization. So Fedosov quantization works if the covariant derivative of the symplectic structure vanishes, and this is basically the same thing because if your symplectic structure has an inverse, then it's a Poisson bivector. Okay, and the Poisson times symplectic covariant is 0. And so if the covariant derivative of omega is 0, the covariant of pi is 0. So in there, somehow it is hidden. But also there are people who defined, you can define a Kähler Poisson manifold with this condition. I don't know what that means. Okay, I mean, I know what it mathematically means. You know, a Kähler manifold is you have a C infinity manifold, a metric and a complex structure, and with that you can build a symplectic structure and so on. So there are certain things in literature that float around this condition, but only mathematical in a sense. I haven't seen a physical application of this. I think this could be something like a non-commutative equivalence principle. But I mean, there has to be more work on that because this is, I mean, for me, it's like, you know, if the covariant derivative of the metric is 0, this is metricity, which is a huge, it's basically the equivalence principle. Then, you know, this would be the symplectic or Poisson analog. But this is just talk. But since, I mean, it's a seminar, so I can, you know, it's not a strict paper, so I can say some ideas that I have here. Okay. So you have this general product, that works out. It works out. So it fulfills all the things we like from a star product, and you can define it for spacetimes that have a Poisson structure that has a covariant derivative equal to 0. And there are a lot of such spacetimes. Okay, for example, so I can prove it for the flat sphere, for the zeta, and so on. There are a lot of, yeah, but unfortunately, I mean, Poisson bivectors are a little bit scarce in that business. Nevertheless, one thing I want to stress is that the generalized Rieffel product is Poisson compatible as well, which means basically if you take f star g minus g star f, you get the Poisson bracket. And actually Dirac already guessed this to first order. So he knew there was some relation with this in quantum mechanics. He saw somehow like the connection between the commutator and the Poisson bracket of Q and P.
Is this equality strict, or is it in the first order in theta? Or
this is just in the for Dirac, you mean?
No, here.
Here it is for the first order of theta.
First order. Okay.
First order, exactly, because second order you get second order derivatives, and this is also, by the way, one condition that is required of a star product in the Kontsevich defines a star product that way, and many others, that it is Poisson compatible, they call this. And for me, why this is important is, like, if we think of it a little bit naively, that the commutator of coordinates gives you the non-commutativity, then the deformation thereof has to be connected to the Poisson bracket, because if you take coordinates xa and xb and insert them into the Poisson bracket, you get PIB. So in a sense, the deformation tells you this automatically. So the star product, the star commutator is defined as this guy, right? So for the flat case, it is just theta u nu, which is just Moyal phi. For the two-sphere has a naturally induced Poisson bivector, so in S2. So the two-sphere, which is this epsilon tensor times x, and this is the fuzzy sphere. This is what people study under the fuzzy sphere. And now I don't know if, I mean, I've asked Waldman if this result is really that new, because Rainer told me to, and he didn't really reply. But I think, I mean, no one has really got the fuzzy sphere from an oscillatory integral in that way. And and now the problem is, okay, I defined this star product for 1 point, but quantum field theory doesn't care about 1 point in a sense. You need 2 points. So you need to generalize this product to 2 points, because I want to apply it to the 2-point function at least, right? And basically it works in a similar manner. The only thing you need to do, you need to introduce a geodesic transport in addition, okay? Because your tangent vectors have to be from the same space. You cannot take two different tangent vectors, basically. You can take them either from Z1 or Z2, from the tangent space TZ1 or TZ2, but they have to be the same. And the point is, this guy only works if this vector is in TZ1. Okay, and so it's a bit technical. Basically, I've tried. So there are 4 different definitions you can do with this geodesic transport. So you can take x1, x and y from TZ1, but they're all equivalent. All definitions in the end reduce to this one. So this I proved also in the paper. So because I was, there's like 1 or 2 weeks, I was worried because there are many definitions. Why this one, right? What makes this one so special? But it turns out that they're all equivalent. So one can prove this actually pretty easy. So it's just like taking a little bit this operator of geodesic transport, the properties of that guy. And I like the idea somehow because in quantum field theory, everything is actually, okay, it's distributions. Okay, but I mean, with proper test functions, this is not a problem. But what is really problematic is when you go to one point, like the coinciding point limit. This is where divergences really start popping up, UV divergences and all that. And the Rieffel product is well defined for 1 point, and I had to define it for 2 points, while the 2-point function is well defined for 2 points, but not for 1 point. So there's this skew symmetry here, and I like introducing the operator of geodesic transport, because I also know, in a sense, that the renormalization of the energy momentum tensor includes geodesic operators. I felt, that this is a good way to go, in a sense. So now we define this. Okay, this is a certain Gelfand-Schilov space, or a Hermander space, where these functions are well defined. So basically, Hermander has given us the amazing result that if you have an oscillatory integral of this form, and you have something chaotic here, then if you can control the chaos of this guy by a certain polynomial growth, then he knows how to well define this oscillatory integral, right? So it has to belong to a certain symbol space, they say. Okay, and then you calculate this product explicitly, and what comes up is that it is basically the normal product times theta AB, delta B prime, and then to second order, you get more things. The thing that is important here, besides, forget about the specifics in a sense. What I want to stress out, up to second order, this star product is made out of a differential operator with smooth coefficients. This is the only thing I need, okay? Smooth coefficients, because theta AB prime is the Poisson bivector, which is smooth, times the geodesic transport, which is also smooth. Here, this thing is theta, smooth. This is smooth, and the covariant derivative in here comes with an orthogonal projector, and the orthogonal projector is also smooth. So everything is smooth here, okay? It's a differential operator, a pseudo-differential operator with smooth coefficients up to second order. And now we apply this guy to QFT, okay? Now, so we have the star product. It runs, in a sense, smoothly, and now we can apply it to quantum field theory in curved spacetimes. A small overview: quantum field theories are rigorously constructed for globally hyperbolic spacetimes. Gira has done his PhD in that and proved explicitly for certain spacetimes that this can be done. The advantages: their existence of direction of time and well post-Cauchy problem. Disadvantages: no preferred state. Okay, which was one of the reasons why I was trained Minkowskian, so I stayed away from this, but actually this is not even that big of an issue in the end of the day, because for a given state, you can do your GNS construction. GNS construction basically means you have a state and a star algebra, and then you put this through this machinery, and it gives you a Hilbert space, a dense domain, representation, and some unique or cyclic separating vector psi. And then the field operators can be defined through this way, and then you define your endpoint functions as the products of these representations as the expectation value with respect to this psi omega. Now, of course, in Minkowski spacetime, there is a preferred state because this is the vacuum. It's invariant under Poincare transformations even. And so it selects exactly this one state. In general spacetimes, you could have a spacetime with no symmetry at all, and then there is no such state. And now, but as I said, it's no problem because actually you have the Hadamard states. And Hadamard states, they resemble the singularity structure of Minkowski. And the equivalence principle basically tells you, if you go short distances and neglect a little bit the curvature, everything looks like Minkowski. Very naively spoken. And Hadamard states are a reflection of this principle that the 2-point function for any curved spacetime should have the same singularity structure like Minkowski. right? So it has a certain definition, you know, a square. I mean, this is the geodesic distance, normalized with an epsilon, and it has a log term and 1 over sigma square. So this is how this thing diverges, right? So in the massless 2-point function in Minkowski is 1 over x minus y squared, right? That is all there is to it. For massive, you get here a log term as well. And so these states you can forget about. You just say, okay, I have no preferred states, but in a sense I have one because these are my Hadamard states, and you can calculate them explicitly for any space-time, and they have the advantage that they capture the singularity structure. So you can define all 2-point functions in the coinciding point limit by taking a 2-point function, subtracting the Hadamard parametrics, and then you have something smooth, basically. And now so the way I define now my Hadamard states or my 2-point functions is, instead of the normal product between these representations, I take the star product. Okay, and nothing very fancy here. I just take the star product between these functions because I know the 0 order, it is the same as the usual one. Now there was one of the I would say best-selling arguments for QFT in curved spacetime, which is this micro-local spectral analysis and micro-local spectrum conditions. So the wavefront set basically of a distribution or of a function is defined to be such that it takes exactly those directions that are not a regular direction for you. Regular direction means that this thing is somehow bounded. Basically, the wavefront set tells you where things go wrong, right? And not only where, but in which direction as well. So some useful properties of the wavefront set: if you have a C infinity function, even the wavefront set is 0, is the empty set. And one thing that will be important is that if P is any differential operator with smooth coefficients, then the wavefront set of PU will be included in the wavefront set of U. Okay, so in a sense, the differential operators do not change the wavefront set. Really, they're included in the original one. And one says a state in quantum field theory obeys the micro-local spectrum condition if the wavefront set is contained in n plus cross n minus, and they are defined as the future and past directed. Basically, for those of you who are only familiar with Minkowski, it means that the singularity structures of those 2-point functions are equivalent to the singularity structures of Minkowski. You have a plus mass shell and minus mass shell, so plus positive frequencies and negative frequency splitting. And Radzikovsky was the first to really prove that this micro-local spectrum condition is equivalent to the Hadamard condition. And in a sense, it is a very strong result because this really justifies why taking Hadamard states. Because in a sense, they tell you that these states are equivalent to taking states that fulfill the micro-local spectrum condition, and the micro-local spectrum condition is basically telling you this state is very similar to the singularity structure of Minkowski. And if you take two different states that obey the micro-local spectrum condition, the difference is C infinity, which basically means the wavefront set of that is vanishing. Okay, and now I can get to my final result, basically. If the state omega obeys the micro-local spectrum condition, which means that it's Hadamard, then the deformed state obeys the micro-local spectrum condition as well. And the reason is a one-liner. So you can think of this paper is basically like the kernel of this paper is exactly here in this one line. The deformed 2-point function I can write as a differential operator of 4th order with smooth coefficients, as I have proven. And this means that the wavefront set so due to this condition, the wavefront set of PU is included in the wavefront set of U. So of the undeformed thing. And if the undeformed thing satisfies the micro-local spectrum condition, even the deformed thing satisfies it as well. which basically means we have defined a deformation, and with this deformation, we could deform our states, our two-point functions. And these two-point functions also see, the equivalence principle. As I said, the p theta is a fourth-order differential operator with smooth coefficients that depend on the Poisson bivector, which is smooth, orthogonal projector, which is smooth, and the parallel transport, which is also smooth. So the deformed two-point function is Hadamard, which means that these deformations are physically really meaningful, since they satisfy the quantum field theoretical implementation of the equivalence principle. And okay, there are certain other things that I can't skip. Let me come to my conclusions and outlook. QFT non-commutative or quantized curved spacetimes agrees with the equivalence principle. So this was important for me to prove that the micro-local spectrum condition is fulfilled. So this is a step 0, so to speak. This deformation can be extended to endpoint functions. And now we have a rigorous framework to examine other achievements in curved QFT and curved spacetimes, like the Hawking effect, quantum energy inequalities, entropies, the semi-classical Einstein equations, and hopefully predict testable quantum gravitational effects. Thank you for your attention.
Thank you very much, Albert, for the interesting and motivating talk. So then we have, according to the format of the seminar, we have infinite time for questions. Okay. So please, the audience, yeah, maybe as a warm-up, I had a couple of comments regarding the use of symplectic structure in micro-local analysis and Fourier integral operators. So actually, there is a thing called symplectic Fourier transform, where you replace kind of the pairing with a symplectic map. It has similar properties to the usual Fourier transform, but then it allows a direct kind of relation with classical Fourier integral operators, right? So it's Hamiltonian and Poisson geometry of the space. It figures prominently in Fourier integral operators as presented in say the 4th volume of Hadamard.
Right.
So it may happen that some of the things that you were saying here, they can be found in a mathematical language where mathematicians didn't realize it has physical significance. This happens very often.
Right.
You are following a mathematician's talk and they are talking about things which you so much expect, but they are talking about these things as like side effects. Right, so it's kind of it's curious that this satisfies this, but come on, this is kind of equivalence principle,
Right.
Yeah, so just to mention that.
Yes, that is a very this symplectic Fourier transformation. So this can be done on non-flat manifolds.
You can do these constructions. In principle, well, the symplectic Fourier transform itself is defined on Rn again because it's kind of a linear form in a function. But the Fourier integral operators, which locally look like that, they can be defined globally if you have symplectic manifold or Poisson manifold where you have Lagrangian foliation, and then you have this Lagrangian submanifolds, and you construct this Hamiltonian flow. So it's basically classical Hamiltonian dynamics now used to construct Fourier integral operators. So in that respect, I love the subject, although I can't say I'm a big expert in it. But I really love how physical constructions and maybe also tacitly physical intuition, although a mathematician like Hermander wouldn't kind of admit that he is deriving motivation from physics, because other mathematicians would kind of frown upon that. Anyway, but this physical insights giving rise to new mathematical structures, this is something I really appreciate, and Fourier integral operators are one such remarkable.
Yes, yes, absolutely. I mean, absolutely. I agree with you 100%. And although I omitted a lot of these details, but I mean, this Fourier integral operator, and he has a paper about this, also like 100 pages or so. This is really in the core of saying why this oscillatory integral is well defined. And so to the symplectic Fourier transform, there is a paper by Varilli and I forgot the other names, but they are famous mathematical physicists from Chile, I think. All Barilli and well, as I said, the name is not coming up.
The recent paper or classical?
No, I think it's 97 maybe, where they define the Fourier transform, the symplectic Fourier transform, the twisted transform, and the twisted Fourier transform, and the twisted symplectic transform. And this is equivalent to the Rieffel product, actually. This is exactly the Rieffel product. Yes, so I've seen this float around exactly, but yeah, now my question is always, how do I curve this in a sense?
Yeah. So the way I understand here is that you basically by using what you call a retraction, you basically map Rn somehow smoothly, but also locally diffeomorphically onto your manifold.
Right.
And then you have the usual Rieffel quantization on Rn. Then you use the pullback to quantize function.
Exactly.
The manifold.
Yes.
One thing that kind of disturbs me is that this Hadamard classes of symbols for which these compositions are defined, the Fourier integral compositions, they are kind of well-defined vector spaces of functions with no nice topology, right? So somehow intuitively, I would love to retain this kind of Gelfand's duality between the manifold as a topological space and the C-star algebra of continuous functions on it. So I'd love to see something like a strong topology algebra for the functions, because it then allows me to recover the points, right?
Yes.
From the Hadamard symbol classes, you can't really recover. If you just think of them as a non-commutative algebra, you can't really, at least I don't know a way to recover the set of points in the manifold. It's kind of the point picture is lost.
Right.
So whereas if we had something like a C-star algebra, then we could go back from the coordinate function description back to the point set kind of description, recover the manifold, claim back the manifold in a sense, right? Yeah, I don't know if there is a way to, maybe a modification or something to enable such a kind of manifold view on this. So if you allow me to elaborate a little bit.
Yes.
So say, if you let's think of, I mean, there aren't many compact spacetimes, but just for simplicity, let's think this spacetime is compact, and all continuous functions then comprise a C-star algebra, a commutative one, and you can think of, by Gelfand kind of transform, you can think of this as the algebra of sections in the trivial line bundle over the manifold. right? These are scalar functions, pointwise multiplication, right? Now, the algebraic deformation procedures like Rieffel and like Kontsevich, all of them, they are of algebraic nature. They take the algebra of functions, they deform it to a non-commutative algebra. If this deformation ends in a C-star algebra, then what you can do is you can look at the Downs-Hoffmann construction and realize the C-star algebra again as an algebra of sections in a certain C-star bundle, right, over a certain base manifold. And then once you know the semi-classical limit h goes to 0, the non-commutative C-star algebra becomes the commutative one, and you can pretty carefully follow how this happens because you explicitly know the deformed product. You could in principle follow how the geometrical side of the things, right? How this C-star bundle gradually deforms into a trivial line bundle over a smooth manifold. And then you can think of this as the quantization of the manifold directly from a geometrical point of view, rather than on the algebraic side. So it would be very interesting for me to see something like that. But starting from Hellman symbols, I don't know how to recover the base manifold, honestly. So do you have any maybe ideas, or maybe it's just
I think
in the sky,
I think this is one of the main issues, right? I mean, also, or the main motivation with this non-commutative geometry thing is, giving some C-star algebra. How can I reconstruct the manifold from it? Yeah, I mean, I rarely have. I mean, okay, there's the con 2-point space. It starts with 2 points, and then you can somehow recover the space by these spectral triples. And there was also some progress done by not Christian Gerard, Wrochner, and so on, and they have done from some Zeta regularization, they have somehow obtained some Lorentzian analog of what Kohn had in mind with these differential operators, how to reconstruct. This is pretty recent. But I have I mean, not no faith, but I don't know how to do these things in that, on that level or that high level of rigor. This would be
I like your approach in that it is explicit, right? You see the quantization in your hands, whereas with Kohn's kind of spectral triples, it's all abstract, where you prove it exists, and then okay, it's hard to penetrate the machinery, even in the simplest cases. So if there were a way to somehow end up with a C-star algebra, say for instance, if you took instead of the Hellman symbols, which are just smooth, you took something like compactly supported symbols, as in the original works of Shubin, say,
yes.
And then these are compactly supported smooth functions. So in principle, you are working with test functions, and then you could complete them with this infinity norm, with the infinity norm to the corresponding, say, C-star algebra, and look if things keep working through that completion. Then if you really end up with C-star algebra, you can try to then look at the spectrum and the C-star bundle and try to do such things, and then maybe also I'm running very much ahead. Of course, these are all technically very hard things, but
yes,
somehow you could then think what the role of the metric then should be, because in a sense, quantum gravity is about the metric being a quantum field, right?
Yes.
And if it is a quantum field, like all other quantum fields, it's not supposed to be smooth. It's supposed to be
C0 infinity,
yeah, kind of
compactly supported.
It's It's supposed to be a distribution which takes values in some operators, right?
Right.
But then this immediately gives rise to some equations like the classical metric produced a measure, right? So the metric measure, and this measure was used to embed smooth functions into distributions. Whereas if the metric is not smooth, the quantized metric is not smooth anymore, it doesn't produce a measure. So you don't know how to go from test functions to distributions, in a sense. Or
but also, I mean, this quantum, I mean, the quantum gravity from that aspect, I mean, you know, it is non-randomizable, right? And I think this is for me a physical argument, you know, why this is probably not the right way to go. Also, the graviton was not really measured up to now, right? So
yeah,
maybe the idea itself of taking quantum gravity to be really take the gravitational or take the metric, perturb it, and then take this perturbation and post quantization conditions on it. I mean, there's perturbative quantum gravity, which makes a bit more sense in that aspect, but that is very physicist technical, a lot of calculations.
Sure. So, but the question still arises: what happens to the metric? Say now you deform the class of functions through the deformation quantization, and then you deform, say, your you forget about the metric. You say it's like a manifold. I deformed this manifold. There is kind of a 2-point function which arose as a weak solution of a metric defined hyperbolic operator, but let's forget about it.
But you're not, I mean, you're not deforming the metric per se, right? You're deforming the algebra of the C0.
That's exactly what I'm saying. That's exactly what I'm saying. So the metric remains in the classical side.
It remains, in a sense, in the classical side. You say it just, I add more structure to it, which is the Poisson structure, basically, as I see it.
So in a sense, you say the classical metric gives a classical operator. This classical operator gives a classical equation. This classical equation has some distributional solutions. Let's take the distributional solution and deform it. Okay, now you have the deformed distributional solution. But when you try to compute the stress or energy momentum tensor of, say, Klein-Gordon field, it includes both the metric and the 2-point function.
Right, yes.
But the metric still lives in the classical side.
Right.
How do you pull metric to your deform? Do you deform the metric as well in the same way? Or you keep the
I mean, not really. Not really. So one way to deform the metric, in a sense, is to add to the metric the Poisson structure. Okay, or I times the Poisson structure, then you have a Hermitian metric, and you know all these and then you have the sort of a complex manifold, and on that you try to figure out what are the Klein-Gordon equations, right? So
why should that metric correspond to the deformed structure?
Yeah, I mean, this is more or less what do you call intuition. So I have some vague arguments for that, but not, I mean, nothing very serious. I mean, Waldman has shown that that you know, you can take the Rieffel product and define as okay, you take a C star algebra A star A, and you define the Rieffel product between them, and then you take an expectation value with respect to some state. The point is that this guy is not a positive state. So it's not a state at all, actually. And so what he did was introduce another operator that makes this positive, this Rieffel product. So his operator on this Rieffel product gives you a positive operator, basically. Then A star A is always positive, or A star deformed product A. And so in a sense, if you you know, see this as a principle, then all that he did was actually take I pi or I omega, and so the symplectic structure, and add the metric to it. And then things work out fine. And then I tried this in quantum mechanics, and some nice things came out. So in a sense, I take this as a principle, but this is only because I'm fishing in thin air, so to speak. I have no real intuition. But what I was going for was I thought to myself, okay, deform the algebra of the test functions, because this is like the idea of non-commutative geometry, and see if the equivalence principle or this microlocal spectrum condition holds, because this seems to me very important. And it did. And now what I want to do is like really apply this to black hole scenarios, or what do you call the energy momentum tensor, so the normalization, and see if I get there some things out that you know you can somehow measure or compare to experiments. So it's I would say it's a very pedestrian way to implement this non-commutativity in a sense to this, but yeah. But it's of course, in a sense, I leave the metric alone, right? I don't say I leave. So yeah, but it's still a non-commutative. Well, okay. There's this work by Doblicher, Friedrichshagen, and Roberts. They defined the non-commutative Minkowski spacetime. Okay. Also, basically leaving the metric alone, and you take just the Hilbert space and you tensor a non-commutative space to it. And then Grosse-Lechner showed that this is equivalent to the Rieffel deformation, basically. So this is my point. So if in a sense the Rieffel deformation is equivalent to non-commutative Minkowski, so if I can do Rieffel deformation, you know, on in a curved spacetime, then this corresponds to a non-commutative curved spacetime. This is somehow I
kind of understand the logic behind this kind of line of thought, but still something makes me uncomfortable is that in a sense, when you quantize the space-time, you lose, or you should lose, the notion of a single point.
Yes, but that doesn't happen. That is exactly that in
the space-time hangs around.
Well, you know what happened in non-commutative Minkowski spacetime, or co-FT in non-commutative Minkowski spacetime, you get phases. The phases in momentum space, they are of the form I, P, theta, Q. And basically, these phases tell you that spacetime is non-commutative, because if you go to small x, these P's become bigger and they oscillate widely, in a sense. So in a sense, it is hidden in there, the non-commutativity from in this physical point of view. You see what I mean? So the Rieffel product between two quantum fields in momentum space in Minkowski basically just gives you phases that depend on this deformation parameter and the momenta, and they make this theory non-free. So you can regard it as an interacting theory in Minkowski spacetime. It is sort of an interaction. And that is the beauty of it, actually, that you can then, you know, really calculate it, and you don't need to throw all of your notions out of space-time and whatnot.
Well, in Minkowski, what you can do, you can look not at the space-time, but at the phase space, say R8.
Okay.
Right?
Yeah.
And then, yeah, if you say, well, I'm quantizing not the space-time, but actually the full phase space. So although the kind of purely coordinate pictures may still remain somehow commensurate, although they shouldn't commute, but the bad things then happen in the momentum side, right? So you can make this, I suppose, work if you can really do this quantization in the full phase space. On the other hand, on a curved manifold, Well, you embed the manifold in Rn, but maybe you need to embed the full tangent space into, and then deform again, like on the tangent space. Yeah, so this is somehow, I mean, I have very vague understanding of this, how this works technically. But the idea that the points in the space-time still stick around, it's a little bit kind of unusual. I would expect them to be replaced by something kind of vaguer.
Okay, no, but you see, this is the advantage of a star product. So you could take classical mechanics and replace the usual product by a star product. And in a certain sense, you get out quantum mechanics. This was the idea of Grunewald, Moyal, Weil, and so on. And then you just have classical phase space, just with a unusual product, a non-commutative product. And this is equivalent to taking this phase space and doing this quantization, in a sense, promoting the coordinates to operators and working on a Hilbert space instead of a phase space. You see, but these pictures, so phase space deformation quantization, or phase space also deformation quantization, I don't know what it's called, or quantization, right? This quantization map is equivalent. You see, but if you would do it that way, so with the deformation quantization with the star product, then it's purely a calculational thing. So, but these pictures are all equivalent, is what I want to say. And yeah, and so doing a quantization, the deformation quantization with the star product is, in my opinion, to first or second order in this deformation parameter easier than taking the whole space-time, promoting those two operators, and trying to define anything sensible on that. Which I'm not saying it should not be done. It should definitely be done. And I've tried in former works in some instances to do that. But I was never sure how do you get back? How do you get back, right? This is the, like, I mean, loop quantum gravity, for example, also goes this route basically. But okay, it's not per se deformation quantization, but proposes quantization rules on connection and holonomy, but they cannot go back to flat Minkowski, which, yeah, I don't know, maybe, how do you say, in old age, I'm becoming a conservatist, but, or more conservative.
So they would say it just means that the theory is not perturbed.
Yeah, okay. No, sure. I mean, right, but I mean, Einstein didn't say that about general relativity, right? I mean, I was saying, I mean, it's not that, you know, he's the highest measure of all, but in the end of the day, you know, Einstein had his special relativity because he knew, you know, there were some principles that were not, like, were mixing, as we discussed once on our way to the Mensa. And I always think about that discussion, by the way. And once, and also general relativity, he always had this Newtonian approximation. So he always knew, like, at the end of the day, I cannot lose this approximation out of my sight, right? And so this is, yeah. So and I would say this deformation quantization to first order or second order is a little bit more in that direction, bottom up, more than, you know, I build something and I try to come, yeah.
Yeah,
Yes.
that's why, in a sense, the limit is called semi-classical, because it's very close to being classical. It's only
Exactly.
first order limit.
Exactly. And if you look at the semi-Einstein, I mean, the semi-classical Einstein equations are also very strong already. They give you a lot of physics already. And what I was thinking, if we can perturb them in some way and still have, you know, some equations of motion and follow, like, what happens with the physical models, you know, maybe something sensible comes out. This is somehow the philosophy behind this approach. But I agree with you. I mean, in the end of the day, what is this theorem called where you construct the spacetime back from the C-star algebra? And I'm not.
Well, I mean, this is Gelfand transform,
Yeah.
right? So you construct it. It's the maximal ideal space of the C-star algebra for a commutative.
Right, for a commutative.
Yeah, for a non-commutative, you end up with a C-star bundle, the Downs-Hoffman bundle.
Right.
Where you have again sections. So yeah, I would imagine that generally speaking, points in the spacetime should become like points in the base manifold, perhaps of the Downs-Hoffman bundle, if you want to be conceptually very consistent, right? So that there are no points anymore. The points are represented by Dirac deltas in the classical commutative case. Now these are other pure states on other kind of algebra, which are not Dirac and therefore cannot be maybe identified by points on any manifold, but it's kind of a space. And then you could put mathematical interesting equations like dynamical system equations. If this space of points is metrizable, you can ask whether it has Hausdorff dimension.
Right.
And as you take H to 0, how this Hausdorff dimension gradually becomes a spacetime dimension, right? It's a very interesting kind of geometrically and functional analytically interesting questions. But I guess these are just too hard right now. That's why people.
There is an interesting ansatz by Felix Finster. An answer. It's I mean, it's developed quite largely. You know, with his causal fermion systems. I don't know if you've.
Which? No, I haven't heard it.
By Felix Finster.
Finster, I know, but
Yeah.
what was the idea?
Causal fermion systems. Yeah, there's also a book about that, which goes a little bit into that direction, I would say. Yeah, so I can only recommend also looking into that. Yes.
So let me write down.
Yeah, Felix Arian, he's well, a great mathematical physicist as well, and understands a lot about analysis as well. And yeah, so he has something similar to that, which he calls a fermionic projector. I think he was in Erlangen, if I'm not mistaken, in that conference, the LQP one.
Was he?
Maybe, but I'm not sure if he has held a talk.
Can't remember. It was 2 years ago.
Yes. No, but I definitely agree with you. So, something like more substantial. I think there is, like I told you, with quantum mechanics and phase space and the quantization map. I think what I'm doing is in a sense, I don't know if isomorphic, but I think there is some map that would
categorical equivalence.
Yeah, there's some categorical equivalence to that. Yes, but as I said, more my approach is in a sense more pedestrian than really mathematically rigorous. I mean, it is mathematically rigorous in the sense that I take care of convergence.
Yes, that's right. So, well, if I had to compute something by hand, I would pick your approach, of course, because there are things to compute, right? So,
yes.
On the other hand, if I had to say impress philosophers for how deep we understand the universe, I would use the other approach.
Right. Yes, definitely. I mean, my so this work I think should be like a zero part, basically. So this is like just formulating a proper language where this algorithms work, and now we start like really examining, for example, this covariant derivative of pi is equal to 0 condition. This has me actually, I mean, yeah, I just got it out. I didn't know what it is exactly, and then I Googled, as a good researcher would do, just to see what does that mean, and there are a lot of notions, and and as I said, what I was thinking, if in Minkowski spacetime non-commutativity means constant, then nabla pi is a non-commutative equivalence principle, because it tells you if I go Minkowski, and which I should be able to do with any curved space-time, then it is flat. So I tried calculating it in the Riemann normal coordinate system, but it doesn't work. So there is something. Then I tried Schwarzschild. I tried Friedman, Robertson, Walker, like explicitly trying to calculate. There's no solutions. It kills itself. So now I'm trying to figure out how can we, generalize this condition a little bit, such that it still holds. So it's still a Poisson structure. It still fulfills this Galton bracket is equal to 0, but with the Levi-Civita connection in the sense. I think this is, yeah.
Another thing that came to my mind is, when you think about just quantum field theory in curved spacetimes, and there is always this issue that how to implement the dynamics on the level of the C-star algebra, and every second or maybe every 2 out of 3 kind of approach assumes there exists a one parameter time-like isometry, which then automatically results in one parameter automorphism group of the C-star algebra, and you think of that as the dynamics, right? So, and at some point I began questioning myself, what if there is no isometry? But usually, even in it's like in Robertson Walker or even in de Sitter, there is no time like kind of there is in de Sitter there is a time like kind of symmetry, but generally speaking, it's too much to ask just to interpret a dynamical system. On the other hand, if you are looking from a dynamical systems person's perspective, a dynamical person would say, well, can I identify the 2 phase spaces at different times? If I can, then I have a dynamical system. So, but the phase space at a fixed time is basically a time slice plus a symplectic form rather than metric.
Yes.
And comparing symplectic manifolds is much easier than Riemannian ones. The symplectic manifolds are much more flexible. There aren't too many symplectic forms out there on a given manifold, right? There are zillions of Riemannian ones, but few.
Yeah, and you have the Darboux coordinates, which will give you everything basically. And I know this is exactly my problem. Like there has to be a marrying of symplectic structures and Riemannian structures in a way that they are compatible. But what is this compatibility condition? This is somehow.
Yes, the Riemannian means potential, means geometry. Symplectic means kinetic, means dynamics, right? So, and these two coexist. But compatibility is kind of a technical thing.
I mean, Kähler is somehow the answer.
Yeah, Kähler is too strong. I mean, it's too
it kills you. It kills everything. It kills everything. You don't have anything anymore.
Yes.
This is exactly my point.
It doesn't exist in that sense.
Right. I mean, yeah. So this it is interesting though. Like in quantum field theory, you use actually. You can define the 2-point function as basically a metric and a symplectic structure.
But the symplectic form is then defined on the space of solutions of the
solution,
rather than still you can give a dynamical system interpretation to your say Klein-Gordon equation on arbitrary globally hyperbolic spacetime using that symplectic form. You identify different Cauchy surfaces with their symplectic forms, and you say, hey, this is a natural geometrical identification, so whatever happens upon this is dynamics.
Correct.
Right? I don't know if something like that helps with symplectic forms, which are just functions of a space-time point, but just an idea in that direction that indeed comparing metrics may be too strict. So if you're looking at dynamics, maybe just comparing symplectic forms could be good enough. And yeah, so things based upon a symplectic structure are pretty natural, although there does exist a metric, and this metric can dominate the symplectic form, as you know, in this one particle Hilbert space structure kind of things, the pure states are those which saturate the inequality and so on. So the Riemannian or Hermitian structure may dominate the symplectic one, but not determine, right? So you may construct things probably from symplectic structure alone, maybe with some mild compatibility conditions with the Riemannian metric. Yeah, so it kind of clicks where.
I mean, this is what I've been wondering somehow, and like if you, I mean, yeah, this scalar manifold, I mean, or a Fedosov manifold, so scalar manifold, you take a manifold, a metric, and a complex structure, and then if the covariant derivative of this complex structure is equal to 0, you have a scalar manifold, and you can define a symplectic structure by G, J, with a complex structure. But the point is, if you would insert any metric that is sensible to a physicist, like FRW, Schwarzschild, like any of these solutions, you get nothing for omega. So there is no such omega. And then I ask myself, I mean,
it's actually, I mean, from one side, I sort of understand why, because there is a big business of classifying invariant symplectic structures on groups, on Lie groups, and there are very few such. So the symmetrists kill your possibilities.
Correct. The symmetrists kill.
That's why I'm not surprised that on Robertson Walker you don't find any.
Yeah, not even Robert. What I tried. Yeah, okay. FRW. So I tried minus dt square plus a square of t and flat. So this is like the dumbest metric, you can think.
Yankee one, they are called. Yeah.
Yeah. Right. Well. Yeah. I mean, you're the expert in Bianchi. I mean, and I yes, the Bianchi. So and so this is the a little bit non-trivialer than flat, right? And then already it didn't work. It didn't work. Like so for symplectic or Poisson, I started with Poisson, I went to symplectic. It all goes to 0. Nothing works there. And it is somehow weird for me, like that this and I don't know if that means you should stop working on it or you should start working on it, because this is
maybe it's like maybe the space picture should come in somehow be your salvage. So whatever is deficient in the coordinate side may be compensated in the phase in the momentum side somehow.
Right.
So if you may have a symplectic kind of form, but for which, say, in the extreme case, the coordinate space is Lagrangian, right? It totally vanishes on it, right?
Right. Yes.
So somehow intuitively, not as a scientist, but as kind of wishful thinking, I would say maybe in phase space picture, you still recover sufficiently many symplectic forms to work with.
Right. I mean, yeah, I think with this compatibility between symplectic Poisson and Levi-Chilita is that as we said, it's Darboux coordinates. There are also a local coordinate system where everything basically in symplectic is flat, right? And this is very much in contrast to Riemannian geometry, very much in contrast. I mean, and I don't even know what is a metric in Darboux coordinates. Somehow, can I like switch this? Is there? Do you know of?
Once again, what do you mean by a metric?
But I mean, I know like if like any complex structure there exists, like this Darboux theorem tells you
Yeah.
you can write it as 0, 1, minus 1, 0.
Yeah.
My question is what, like if I have a Kähler manifold, which basically means I can define a metric or symplectic structure by a metric, how does the metric then behave under such a coordinate system?
The problem is that the symplectic form doesn't restrict the metric too much.
Yeah. Yes.
Right? So basically your metric can be written the symplectic form composed with this J almost complex structure, and the J just remains. So you get J because in Darboux coordinates, the symplectic form becomes just diagonal or cross diagonal 0, minus 1, 1, 0, say.
Yes.
And then you're left with your J, the almost
Right.
complex structure, which
Yes.
can be arbitrary, a smooth
Right.
field.
Right.
That's it.
Right. Yes.
There are just much more freedom in a Riemannian metric than in a symplectic structure.
Yes. Yeah, the symplectic structure is way more rigid. You're right.
Other members of the audience have questions for Albert, please.
I had a very vague and general question. So when you said that you intend to find some things that you could test, like gravity-wise, like
Yes.
something physical, do you have
Yes.
something specific in mind?
Yeah. So I have quantum energy inequalities in mind. So that like you can with quantum field theory, you can also generate quantum energy inequalities that bound basically the possibility of exotic geometries, and they go into singularity theorems and so on. And I applied some of these techniques already to them, and this would give me some physical answers, so to speak, about, for example, time travel, wormholes, and so on. This is a seminar, I can say whatever I want, right? So, this is all like hand wavy still. So what I would like to have is a wormhole solution that has no negative energies. So a traversable wormhole solution with no negative energy. And I think non-commutativity these non-commutative structures applied to it could give me such a thing. But this is, this is just on a level of speculation at this stage. Another thing is, you could, what people do is take the semi-classical Einstein equations. So, there's these Einstein equations, and on the right-hand side, you take the expectation value of T mu nu, and then you calculate in a sense, and then you have even order of H bar, so to speak, different than the classical energy momentum tensor. And then, you get all these inflaton and all these nice inflationary cosmology effects from that. And what I want to do is I want to apply these deformations to the T mu nu, so take the expectation value, but with respect to these deformed states, and get a second order in H bar, different term from the usual one, and then see what does this term do to the quantization somehow. And so you have a little bit of a test run, so to speak. So this is, yeah. So basically, actually, just semi-classical Einstein equations. Can I apply my deformation there and get something sensible that is not instantly ruled out by physics? And also, there's these whole things with relative entropy nowadays. So a lot of calculations in quantum field theory with regards to relative entropy, where I also want to, we did, and this should come out very soon, apply these methods to the relative entropy and see, does it do something very crazy so that we can exclude it instantly? So what I want to do now is basically, as they say, the chess player offers a gambit to win the game, the mathematician offers the game. But I'm not a mathematician, so what I want to do is be like a real physicist about it, like give the theory the knife and stab me if you're prepared to do it, like kill it or don't. So but up to now, like the results are looking good. So so also like Hawking's entropy, there have been papers where they calculated the relative entropy or the entropy of black holes with with regards to this Hawking entropy formula. And what I want to find out is if I apply these methods to the entropy formulas, will I get logarithmic corrections, for example, that are predicted by string theory and by loop quantum gravity and so on, rather loosely. And I want, but yeah, in the end of the day, as Gira, we were trained like with this East German way of really doing the calculation. So I want to see, does it give something sensible or not in these contexts? Yes.
Right, very interesting. So I mean, one sensibility check of consistency with quantum mechanics, right, could be, for example, you take two states, right? You stay in one point in space-time, you compute the relative entropy between two states, and then you take your system on a closed loop, you come back, you have done some operation, some quantum operation on your states, right? And then you check the relative entropy. If it decreased, it's good. If it increased, then something
exactly. Exactly. This is that's a good thought experiment. Yeah, this could be. I mean, okay, quantum mechanics is I don't know how to do that for these systems. I just know how to do it for quantum field theory.
All right.
So but something similar, similar thought experiments we will have to do. Exactly. Does this thing decrease or increase, or does it give me a negative relative entropy?
So actually, in quantum field theory, we do know it. I mean, locally or microscopically, it fails already at the level of evolution, right? So at a single point, the energy density can go as negative as you wish.
Yeah, but this is where the quantum energy inequalities come into play.
That's what I wanted to stress here. That so entropy can kind of decrease at a single point as arbitrarily as you wish. But when you take the average over a finite volume, then the thermodynamical laws in this averaged form still hold, and these are called quantum inequalities. And these are good tests indeed. So if you do your, say, deformation, do you still have these properties? Do you still obtain this averaged thermodynamical laws?
In flat space-time, I still have them. So there's these quantum energy inequalities by Fewster in flat space-time for the Klein-Gordon field. I still have them. Good. It is actually bound by the same. So yeah, that was a consistency check. I calculated the relative entropy for these non-commutative fields, and that actually gave me even a meaning for this deformation parameter theta. It is equal to the Planck length squared. That comes out instantly. Yeah, that was also a nice one.
Great.
Yeah. And if Rainer corrects the paper in a decent time, maybe you will also read it in a decent time, but it's still stuck at the boss,
That's an asymptotic statement, yeah.
Yeah. So yeah, these things have to be checked. Yes.
So further questions, please.
Well, just a related comment. I mean, so far as the effects of energy conditions are concerned in general relativity, the most pressing problem, I'd say, isn't that you don't have any wormholes, but it's that the theory, classical general relativity, isn't consistent in the sense that you start with some nice initial conditions, and you develop generically singularities whenever you have gravitational collapse. And so I'd say the first thing to check is the Schwarzschild solution, not the Einstein-Rosen bridge, to see if you can solve
the Schwarzschild solution.
The general theorems. I mean, saying that you have to make singularities whenever.
Absolutely. I mean, so we're going to this wormhole solution. I would. So what I wanted to check is the how do you call this? The not the one by Einstein-Rosen, but I think 76 by Morris Thorne. They have these this traversable wormhole solution, where basically you have two asymptotically flat spacetimes, and they're connected by this wormhole. And in the middle, you have now in the throat, you have these negative energies, basically.
Yeah. Thorne called them exotic matter. There's just something.
I'm just a big fan of time travel, so this is why I wanted to check if this can be somehow done. And
Thorne was my GR teacher. He would draw these things on the board. He really got into this. So.
It's very, very interesting, actually. All these things, and I mean, the Einstein-Rosen bridge you cannot really travel through, right? It's just a black hole, so you die in either end somehow before you even reach. But a traversable wormhole solution that already would, in my opinion, be for me like a proof that I'm going into the right direction. But of course, there's all these singularity theorems and so on. I don't think, or I don't know how this would be touched upon with this deformation quantization, or if at all, because as Yerevan said,
you leave the metric as it is, right? So
I leave the metric as it is, exactly. I just do quantum field theory with these deformations. So in a sense, on classical GR level, I don't think anything changes there.
Is it that the wormhole? I mean, so your plan is to take the Kip-Thorne solution for the wormhole, but you're not going to put in the exotic matter, or how is it you're going to make it traversable?
No, I would
put in exotic matter.
So first of all, what would one do when calculate the semi-classical Einstein equations for this solution? This has also not been it has been done, but and see the consistency there, and then instead of the usual states, I would put in the non-commutative states and see if the energy momentum tensor then really has to be negative.
Okay, but in the case of these general collapse theorems giving you singularities, the whole problem is the energy momentum tensor. I mean, if you didn't have these energy conditions, then you wouldn't necessarily get collapse to a singularity.
Right. I mean, but in quantum field theory, you replace the energy momentum tensor by the averaged energy momentum tensor, which is somehow weighted by these.
The question is valid in a sense. I mean, indeed. So the proof of this singularity theorems relies on the kind of common sense inequalities coming from the matter, right? So there are some assumptions on the structure of matter, some kind of positive pressure, energy response, and so on, these kind of things. From which Penrose and other famous prominent people got their prizes. Now, if the deformed energy momentum tensor fails to have such properties, then you may be able to actually circumvent singularity theorems. So it may happen ideally, or maybe not, I don't know. It may happen that this singularities just appear as a limit in the limit as theta goes to 0.
Right.
That also might happen. I don't know, no idea, but theoretically, right?
I mean, so my vague idea is why I think that this should be true is because if you think of as non-commutative structures or this quantumness of space-time, it only happens when space-time gets confined to a small area and there's a lot of energy, of course. And this is exactly what happens in the throat of a wormhole, so to speak. And so in a sense, the quantum nature of space-time would have to fight against, this thing, and this would give you positive energy condition. As I said, this is very, I'm just, talking this is just very intuitive what I think might happen, and with this construction I hope I can really tackle these questions and see if it happens or not. I mean, this is in the end of the day, the math decides our fate, so to speak.
So maybe I missed it, but did you talk about, here the construction was this embedding of the curved space into flat space, which obviously isn't unique, maybe unique up to something. So did you talk about how the constructions depend on this choice?
Yeah. Well, no. This is a very good question, actually. So I can show you. So I have this result that I skipped, actually. So basically, if the deformed states, so you have two deformed states that can be defined using either two different isomorphic embeddings and retractions. Okay. So this is what the prime here denotes.
Yeah.
And the deformed 2-point functions, omega-2 and omega-2 prime, have the same wavefront set, actually. So basically what I'm saying is that the singularity structures of those 2-point functions are independent of the chosen embedding and retraction. And in a sense, explicitly they do depend on it, but for the important step here, they don't. And the reason is that their difference is smooth functions, and thus the wavefront set is equal to 0, and then these things follow. So
they contribute something in after the regularization. Say their singularity may be Hadamard, but maybe when you Hadamard regularize, one of them gives a different value than the other.
yeah,
Say,
I mean, but it's C infinity. So
yeah,
of course,
but you are taking the C infinity, right?
We're taking this. Yeah, of course. That can in the end interplay there. Exactly. I was actually hoping that when I come to the wavefront set, that it will tell me which embeddings and retractions are allowed or not. I was hoping that this gives me actually the conditions on those, but unfortunately it didn't, or unfortunately I don't know right now. But of course, I mean, yeah, it will in the construction in the end. Whenever you embed, depends on embed. I mean, I could, instead of a sphere, you can do it with this x square plus blah blah, or you can do a what do you call this other embedding? What is it called? Spherical projection, right? Is it called a spherical projection? You know what I mean?
Stereographic?
Sorry?
Stereographic projection?
Stereographic, sorry. Yes, stereographic projection. So you could also do that projection, right? And see how far you get. So and that will give you a different deformed state, of course. But yeah, in the end,
weird, yes. If you don't mind, sorry for interrupting. I guess different retractions might, just due to global topology of the trajectories, might give not non-isomorphic algebras after deformation, but otherwise different embeddings should give isomorphic algebras. And once you have, I mean,
but the point is, I'm not actually touching the algebras per se, right? So I do GNS construction, and then I implement the star product. So
yeah, on that level,
after the fact, yeah, on that level, yes.
Yeah, so because particular functions may swap their roles as physical quantities when you change coordinates.
Right.
Right, you take a different embedding, and
Right.
now you have to come up with some automorphism of the symbol class, say, which corresponds to the change of coordinates.
Right.
But I guess just the trajectories of these retractions, if some of them kind of have conjugate points and others don't, say, you may end up with non-isomorphic algebras, some topological effects, which might be even measured somehow. I don't know.
Absolutely. Yes. That is a very good remark. Yes.
It's just kind of an alarm bell because every GR class says every couple of weeks that's exactly what you're not supposed to do. Never embed in a bigger space because you run into this trouble. And so,
right.
Then in the end, sometimes you have to do it. I mean, you have all this anomaly inflow and stuff where you die if you didn't try to make some higher dimensional space. But
right. Yes, I agree. In general relativity, this is a bit frowned upon. Right. But yeah, I think, I mean, in the end of the day, the physics should not depend on the chosen embedding or retraction. But what classifies physics now? That is, and I mean at that stage I classified physics as this microlocal spectrum condition, and that didn't tell me still a lot. But this is really an extreme actually, because it just tells you that the singularities are alike as Minkowski.
Yeah, it tells you that ultraviolet asymptotics match.
Exactly.
Yeah,
But at moderate scales, they may be different.
Yeah, so there's no question of the asymptotics, because you could embed in a tubular neighborhood. Nobody complains about embedding in a tubular neighborhood. The problem is if you try to make something global, which connects it, and there's some choices.
Right. Yes.
The global topology may encode physics, actually, as it does in many other occasions, right? So
Yeah, so that's how the argument always works. So it would encode physics, then we have these tests, and it's excluded. And then you try again, and it encodes some different physics, and you do some tests, and it's excluded. So the problem isn't that it's trivial, it's that it's not trivial, I mean.
But it's not always excluded. Say, I mean, the choice, I mean, it took mathematicians, I think, some 5 or more decades to finally realize that, say, the arbitrariness in the choice of boundary conditions for the eigenproblem of a differential equation or a differential operator cannot be solved mathematically, because these boundary conditions dictate the physics. So they were suffering with this zillions of different self-adjoint extensions of the same densely defined operator in quantum mechanics, trying to come up with something that singles out a single kind of unique extension, until they realized this shouldn't be done, because different self-adjoint extensions are different physical systems. And it is the physicists that should tell you which one to take.
Yeah. So I'm not making a general argument against auxiliary information in theories. It's just a specific thing about embedding spacetime into Hebbian spacetimes that every teacher tried to drill into their students. No, you're not supposed to do this.
I mean, it's kind of, in a sense, contrary to the spirit of differential geometry as such, and the ideas of manifold. But if these embeddings are diffeomorphically equivalent to each other, then I agree. But if there are topological differences between these embeddings, because it's not, well, the embeddings probably not, but as I said, say the retraction maps, if they are not diffeomorphic, if they are topologically different, then no geometer would argue that they should be the same. Indeed, I mean, people would say, you know, people like Atiyah Zinger, they got their Fields medals for their index theorems. And the index theorem is just something about what happens very far because of some boundaries, right? So
I mean, there's also in quantum field theory, there is this work by Ferch and Friedenhagen Bonetti about the local covariant quantum field theory. And there they basically, they use the category theory language, which I'm not very familiar with, but they basically prove that there is a connection between quantum field theories on different spacetimes and spacetimes that are connected by isometric embeddings, in a sense. And my hope is, you know, to somehow imply those things or apply those things to that categorical approach.
That's why I said I expect different coordinates to give you kind of isomorphic algebras. So
yes, so their argument is if you have a category of globally hyperbolic spacetimes and they are connected by these isometric embeddings, you can define to each of them an algebra, a quantum algebra of quantum fields, and these algebra of quantum fields are related by some unitary transformation, I think,
isomorphism
or isomorphic, yes, action. And so in a sense, the physical data is very similar in a sense.
You think of that as canonical transformation in a sense, right? So it's a canonical transformation.
Yes, it's a So in a sense, QFT in curved spacetimes and general relativity, while connected, you know, one cannot draw the same lessons but sometimes similar. I mean, similar things happen to the renormalization of the energy momentum tensor, right? I mean, there are different ways to go about it, and then Wald wrote this axiomatization of that, which complies with general relativity in certain senses, but extends it also. So it's a very maybe narrow perspective on general relativity. So maybe I don't know.
At the beginning of the talk, you said that quantum gravity and curved spacetime should be a first approximation to. That quantum field theory on a curved spacetime should be a leading approximation to quantum gravity. No, this was on a slide somewhere.
Yes.
So what kind of approximation is this? I mean, it's not an expansion in. You mean an expansion in G Newton, or what?
Yeah,
leading
in H bar or the Planck length, exactly.
So what about just graviton loops, which aren't connected to anything? I mean, they don't come into quantum field theory in curved space. They don't have any factors of G Newton. And this is kind of the argument in the preface of Brill and Davies. It said the rest of this book, we make this claim, but here's Weinberg's argument that it doesn't actually make any sense. I don't know. But that was the early 1980s. So maybe since then, people have come up with an answer. I don't know.
Right. Yeah. I mean, this is sort of, how can I say it? I mean, a lot of effects that we have, like the Hawking effect and the Unruh effect, these particle interpretation, cosmological applications, with the inflaton and so on, they come from QFT and curved spacetimes, basically. So the zero or maybe
none of these are observed, though. No, I mean, it's a really developed field with no observations. So
well, I mean, yeah, the Unruh effect has to be still measured. Particle interpretation, I mean, this is an interpretation question, so you don't have to really measure it, right? I mean, it's clear.
I don't know.
Well, you know what I mean? This thermal this thermal interpretation of quantum field
particle creation.
A particle creation or annihilation, you do the splitting, but if you accelerate, then all of a sudden you have this thermal bats flying at you. So this really sort of questions, even in Minkowski spacetime, if you go to Rindler, then these things happen, which is basically the Unruh effect. But you're right. I mean, the inflaton and these inflatonary phases and so on, when you do this quantization in the semi-classical sense, I think there has been some measurements there, right?
I mean, you do measurements usually in a system which you argue is equivalent. I mean, it's very. I'm not sure exactly which measurement. You mean the ones in the optical lattices where you're trapping particles and kind of saying it's a one-to-one map to that system, or which measurements you mean?
Right.
Because I mean, okay, you say it's equivalent, it doesn't really mean that it's equivalent. It's I mean, they're not doing general relativity there. They're doing electromagnetism.
Of course, yes, yeah. I understand your point of view. Yes.
So, yes. I don't know. Okay, anyway, I was just wondering in the last 40 years, my information's all very old.
I should have said,
so I don't know what.
It is common folklore that people think that quantum field theory in curved spacetimes is a zero order approximation, because I mean the way I would think of it, you have quantum gravity, and then in some limit you get quantum field in curved spacetimes out, because if you stop the curving, so if you make the curving flat, then you get quantum field theory in flat Minkowski spacetime, which is well observed, right? So in a sense, so quantum field theory in curved in flat space, quantum field theory in flat spacetime is a limit of curved theory, because I mean you just set the metric eta, and then you get the standard model, which is well observed.
Yeah, no, quantum field theory in flat space is great. I agree with that.
Right, and it is exactly the stance that I used to have when I was a PhD, and I would argue with Yerevan about this point. But yeah, I mean, I still think that quantum field theory in curved spacetimes has its merits, right? But of course, I mean, yeah, a measurement would really help. I agree with you 100% there. There is no question about that.
I guess if you are to ever perform a measurement of quantum gravity, it is sooner gonna be a measurement of, or rather a measurement of gravity plus quantum. It's most likely is gonna be a measurement of classical gravity plus quantum field, because quantum gravity is much, much harder to observe, right? So if you have an observation, much sooner, you're gonna observe something related to quantum field plus classical gravity, because quantum gravity appears at more extreme circumstances, which are hard to come by. Right?
Okay.
So, and the quantum field theory in curved spacetime is the theory of classical gravity plus quantum fields.
Right, but I mean, that isn't necessarily unique. So the claim, which is a claim people always make, is that the leading order approximation to quantum gravity, the leading order in the sense of perturbation theory and G Newton, is quantum field theory in curved space. But on a theoretical point of view, it's not clear to me because you have graviton loops which don't show up in one, and they're not in order.
Then you can forget about fields and say, okay, do you think general relativity or the concept of a Lorentzian spacetime is a zero approximation of quantum gravity or not?
Well, zero approximation, you have to say zero approximation in something.
In a certain parameter that describes the quantization of the spacetime, I don't know.
I mean, so a parameter which describes the quantization of spacetime, it could be G Newton. I mean, but on the other hand, that's a dimensionful parameter. So you need something dimensionless. So you can do something dimensionless, and then you get to an effective theory point of view. And then you get all these people. I saw a seminar. I went to a conference with Rieffel last week where he was arguing, no, you should never do that. And he's done this swampland program for 20 years where he says that's exactly the wrong thing because it's not internally consistent. I don't believe in his program, but I mean, the argument that it's not internally consistent to use effective field theory to describe gravity is kind of convincing. Because you get the paradoxes which I can't explain.
If you invalidate general relativity in the first place, then of course you forget about quantum field theory in curved spacetimes, where curved spacetimes are general relativity, if you wish, right?
So general relativity gives you curved spacetimes, and general relativity works in every situation which has ever been measured. So does that mean it works in every?
Relativity is defined in terms of spacetimes.
Yeah, it's defined in terms of spacetimes, and it works in the situations which are measured. Now the question is, how do we put it together in quantum field theory? Every measurement that I know is one or the other.
Sorry, wait. Quantum field theory, leave it alone. So you have quantum gravity on the one hand, hypothetically, and you have general relativity. Now, do you admit that the general relativity is the zero order approximation of any quantum theory of gravity?
I don't know what zero order means. So zero order in what? And how do you do the expansion?
Theory has an order defined.
In H bar, you want to say like something like so you want to go to the classical limit.
Well, H bar is dimensionful. So it needs to be, and H bar is equal to 1. So you can't really be zero order in H bar.
Divided by something that has action.
But the trouble is, so normally you say divided by whatever scale you have, but in quantum gravity, you always have a mixing between UV and IR. And so if you say divided by some scale and then you get small, well, once you get to be small, well, then you're in the UV. And again, you don't trust general relativity. On the other hand, if you get to be big, well, big in gravity corresponds to high energy. And so again, you're at high energy, you get past the Planck scale, you don't trust it again. Yeah, so it's not clear to me if there's any limit where you really trust it, where you trust general relativity.
But the question is not really addressed to quantum field theory and curved spacetimes. It is addressed to the general relativity as a classical limit of quantum field theory, of quantum gravity. Here is the question. If you think that general relativity should be, in whatever sense you wish, the classical limit of quantum gravity, then it is only natural to add quantum fields upon it. That's it.
So I don't know how to take any limit of a theory if I don't know the theory first. So in quantum gravity, not knowing quantum gravity, it's hard for me to imagine what it means to take a limit.
I mean,
would you agree that
you don't have to be able to define it before operating with it, right?
I do, maybe because I'm a physicist, but I mean, I need.
You would agree that quantum gravity, let's say it is governed by H bar C and the Newtonian gravitation constant. It's in some limit it has to give you quantum field theory in Minkowski spacetime, right?
Well, some limit. I'm not sure if it works all the way to the limit because you go all the way to the IR and then you start getting these, long distance effects, which.
Okay, let's say there is one path to go to.
So I don't know if it's a limit. I mean, there's a regime where general relativity is a good approximation, but I don't know if there's actually a limit where it becomes perfect. So in the case of normal quantum field theories, no gravity or anything, there really is a limit where it works. So if you take,
I mean, if I take quantum field theory on flat spacetime and I restrict it to finite particles and I go non-relativistic, then I get quantum mechanics, right?
wait, say again? No, I missed the beginning of the sentence I was thinking of.
If I take quantum field theory in
Yeah.
Minkowski spacetime or
Right.
in flat spacetime and I confine the number of particles and the speed gets slower and the energy not that high, I should go to quantum mechanics, right?
Yeah. So this limit I know how to do.
And then
I like
quantum
this limit.
mechanics, I can go to mechanics as well by the IFS.
I know how to do this limit too. So I'm happy with those two limits. But on the other hand, I know the theory that you started with, so that makes it easier.
I see. Okay, but this is exactly. I mean, this is a how do you call it? A hypothesis, basically, right? We're
But it's a
operating.
hypothesis. But hypothesis is usually you have some setup. I mean, and then you do hypothesis in that setup. So
But
here
I mean,
you're taking a
up to
limit of
now,
something which
all
you don't.
our theories are such that they contain the lower energy or low weaker theories in them, right? It's like a onion system.
You said it first the way, I mean, then you changed your words carefully. So all the theories were the lower energy ones. And now we've got quantum gravity, which has the UV-IR mixing. And that's the thing which I think throws you.
I see.
It's going to lower energy means going to longer lengths, which means going to higher energy.
By the way, in non-commutative quantum field theory, there is also UV-IR mixing.
Yeah, and so I'm very confused there too.
That you can cure, by the way.
Yeah.
So there is a cure by renormalization techniques that you can do, such that these mixings couple, and then you can treat them separately.
Yeah. So there was a wrong paper by Seiberg. It's a very dangerous thing, but now I guess it's sorted out. So
I mean, it has some merits in quantum field theory in non-commutative quantum field theory. For phi to the 4, for example, if you put star products in there, you see that the propagator has some terms where p to 0 or p to infinity, they both diverge and they mix somehow. And there's then some papers by Grosse and Vulkenhaar that prove that you can actually renormalize this, and in a sense decouple those mixings. I just wanted to mention that.
Yeah. So if there was a similar result in quantum gravity, I mean, that could change everything. So yeah, no. So I don't know. I mean, I'm just wondering where people have been working on these, and I haven't since I was a student. So, and for me, I really don't understand anything with massless particles. Maybe Streeter and Whiteman just made all the particles massive, and so they could treat everything. Then it turned out QED, when you try to put in massless particles, okay, there's a whole story of Fadiev and Kaldish, and now rebranded his memory, which makes, life is much harder with massless particles. In QCD, because of the massless particle, basically nobody knows how to proceed. But the basic idea is once you have a massless particle, then anything you do to it, it's going to take you out of the Fock space. I mean, you'll be out of a finite number or Fock space.
Right.
And so just all the tools that I know just don't really work once you have massless particles. And so anything could be there in gravity. I don't know. I mean, if already the gluon's too hard for me.
Right. But why don't, I mean, so what would be for you a counter argument that QFT in curved spacetimes is a zero order, or you say there are no approximations for quantum gravity?
It's not obvious to me from dimensional analysis that there have to be. And also, if you're just using G Newton, I don't know what to do about the graviton loops, which don't have any powers of G Newton and aren't there in quantum field theory and curved space.
Right. Okay. I see.
I mean, another counter argument, like a very vague one that you could think about, is that like if you have a curved space, then your gravity is very strong, right? And if it's very strong, then there is no guarantee that you can just consider ordinary quantum mechanics, but just curved, I mean, why would you?
Yeah, that's the usual effective field theory logic, and I mean, it works sometimes. Yeah, so I mean, we know, you can look back in time, and so you're doing a lot of redshifting, and it seems like the physics is the same. I mean, we look at plasma physics in the CMB, the decoupling temperature is the same, and you're redshifting by a factor of 10,000 there. So some very basic things which could have gone wrong haven't gone wrong. Well, that doesn't mean that some other basic things aren't going to go wrong.
Yes, everything that could go wrong will go wrong at a certain point. If I learned anything in the last 20 years. Yes.
That's the hope anyway. That makes life more interesting if we can observe something going wrong.
Right. No, I think this is an absolutely valid point. Yeah, and yeah, one should put this in the back of one's mind.
I want to thank the speaker once again and everyone for this very enjoyable discussion.
Yes.
And this ends the formal part of the seminar.